Questions 8 through 10 on the 2005 Grade 12 Euclid Math Contest. A function is defined by f at x is equal to 4 if x is less than negative 4, negative x if x is greater than or equal to negative 4, or less than or equal to 5, and negative 5 if x is greater than 5. On the grid in the answer booklet, sketch the graph of g at x, which equals 25 minus f at x squared under the square root sign. State the shape of each portion of the graph. Let's make a table of values of x, f at x, and g at x. And then once we have this, we can start plotting our graph. G at x, they have given us as being equal to the square root of 25 minus f at x all squared. And we can therefore use that equation to factor our values of x and f at x. So here we go. First of all, how far am I going to go here in terms of my x values? Well, look at down here, our range. X is less than negative 4 is always going to lead to 4 as a value for f at x. So I think all I really need to do is just put in a couple values just to get an idea of what that graph will be like when x is less than negative 4. And then negative 4 all the way to positive 5. So those ones, I'll just put all of those in, just the integer values. I think that should be sufficient to draw this graph. And then once I get to positive 5, if x is greater than 5, it's always going to be negative 5 as the value of f at x. So just a couple of those is enough, I think, for that part of the graph. So 6 and 7. And I think that's it. That's all we need in terms of our values of x. So we've got two categories really, or three categories actually. So here we go. Let's start plugging in. The first one's when x is less than negative 4, f at x is just 4. So that's easy, right? When it's in that category. So we just figure out g at x. G at x is going to be 25 minus f at x squared. So that looks like 16, square root. And that is 25 minus 16 is 9, so that's 3. So therefore g at x is 3. Okay? That takes care of that. Let's do this one next. Instead of going into the middle part, let's do that part next. When x is 7, f at x is just negative 5. And when x is 6, f at x is also negative 5. Okay? So now let's figure out g at x. That's going to be 25 minus the square of f at x, which is going to be 25, negative 5 squared. And that is 0. So there you go. We've got that section of the graph. So far, so good. Now let's concentrate on all of these values here. And for that, it's actually pretty straightforward for the value of f at x. It's just negative x. So for example, when x is negative 4, f at x is 4. And similarly, when it's negative 3, it's 3. You're just taking the negative value of x. And then when x is positive 1, f at x is negative 1, negative 2, negative 3, and like that. Okay? So just straightforward from the definition of the function. Now calculate g at x. A little bit more work here, but that's okay, not a problem. Let's figure out g at x for this guy right here. 25 minus 4 squared, which is 16, under the square root sign, and that is going to be 3. When f at x is 3, we've got 25 minus 9, all under the square root sign, and that's the square root of 16, which is 4. When f at x is equal to 2, we've got g at x is equal to 25 minus 4, square root of that, square root of 21, and the square root of 21 is approximately equal to 4.58. So I'll put that in there like that. And then for f at x equals 1, we've got g at x is equal to 25 minus 1. So we've got the square root of 24. And the square root of 24 is approximately 4.89. Okay. And then when f at x is 0, g at x just becomes 25 under the square root sign, which is of course just 5. So that's good. And the good news is for negative 1, that is just going to be the same as 1, because when you take the square root, the value is the same of that expression. And then for negative 2, it's the same as 2. And for negative 3, it's the same as 3. For negative 4, it's the same as 4. And for negative 5, it is the same as these guys, which we just did, 0. Okay? So there you go. We've got all our points. Now let's graph this. So first let's put in our values. We got a range from about -6 to 7. So let's plot those in. Well, when x is -6, which is right here, or -5, we've got a value of 4 for f at x, and we've got a value of 3 for g at x. So we're plotting a graph of g at x. Sketch the graph of g at x. So on this graph, we've got g at x up here, and we've got x here. Okay, so let's plot the value for g at x for -6 and -5. And there you go. It's just both of them are 3. So basically what that means is that you're going to have a line that just keeps going like that all the way to infinity, I guess, going in the right direction. So that's just the line, because they want you to describe as well. State the shape of each portion of the graph. Okay, well, this is just a horizontal line. So I'll just draw that here. Horizontal line. I guess that's what they're asking for. Okay, let's do the other part, the easy part, which is these guys here. When x is 6 and 7, our value for g at x is 0. So that's pretty straightforward. That means here and here. And it's also 0 for x equals 5. So I'll put a 0 there as well. Okay, well, that's pretty straightforward. That's also a horizontal line going that way. Correct? Going that way until infinity in the right direction. So I'll put that as well. Horizontal line. Now we have to concentrate on the middle of this graph. Let's plot in the values and let's connect the dots. So here is the dots, and if you connect them, it'll be basically something like this, all the way coming down to that. Now we have to describe what is that shape. Now I can call it a curve. I can call it a, I don't know what they really want. But one thing I did notice in this graph, g at x, is that if you call g at x y, and let's say you called f at x x, this is essentially what you would boil down to. And if you take the square of both sides, you get y squared is equal to 25 minus x squared. And if you put everything on one side, you get x squared plus y squared is equal to 25. And that's a circle. It's a circle that's centered at the origin with a radius of 5. Now, because we rearranged it and took the square root, that means that y always has to be greater than 0. And that's why there's nothing down here. And also, this is only true for this range here. So basically, if you wanted to describe in words the shape of that curve, it's just part of a circle. So a section of a circle, I guess, would be the way you would describe it. Instead of saying curve, you say section of a circle. Circle of radius 5, I guess. Okay? So that's essentially what they want in this question, and I encourage you to do this on your graph paper and see if you can get this just the way I did. In the diagram, two circles are tangent to each other at point B. A straight line is drawn through B, cutting the two circles at A and C as shown. Tangent lines are drawn to the circles at A and C. Prove that these two tangent lines are parallel. This is the first tangent line, and this is the second tangent line. So before I begin with trying to prove that, first let's try to understand a strategy, right? Instead of just kind of going in an unknown direction, uncharted territory. What are we going to do? We have to have a plan. And the plan is obviously to show that they are parallel, but how? How do we show that two lines are parallel? Well, there's several ways. One way is to show that they have the same slope, I think. The other way, of course, is to use angles. And I'm going to use angles. So if you have two parallel lines, right? Let's say you have a line like this, and then you have a line that's parallel to it like that. If you were to draw a line between those two, if those two lines, original lines, are parallel, then these two angles will be the same. So for example, if that's angle X, this is going to be also X. And that is known as alternate angles. And alternate angles, when you have parallel lines, will be equal. So there you go. That's our strategy. Now they've exaggerated this. They've shown these two lines in such a way that they don't look parallel at all. But we have to show that they are indeed parallel. I think they exaggerated it just to make it less obvious for us. Less obvious for us to kind of look at it clearly. In our minds, we would think, well, there's no way those are parallel. How can I prove that? It just makes it a little bit more challenging, I think. But that's okay. We can do it. And I'm going to do it exactly like this. So here we go. Let's blow this up a little bit. So let's label a few things to help us in our proof. The first thing is I'm going to draw a line from the center of the big circle to A, like that. And I'll extend that line from the center to B, so like this. And I'll do the very same thing for the small circle from the center to C, and I'll extend that line from the center to B, like that. Okay? And anything else here? Well, these are tangent lines, right? These guys. These are tangent lines. So that means that this is a right angle. That's basically the definition of a tangent. So this guy right here, this is a right angle. Okay? I hope you can see that what I drew there. All right, now let's label some things here. Let's call the centers, well, C's already been taken, so I'll just use O. O1 and O2. O for origin, I guess, but that's not a proper word to use in this case, but whatever, O. Okay, now this angle in here, I don't know what it is, so I'm just going to call it X. And let's see what else here. This is 90 right here, correct? So this whole angle from here to here, this whole thing has got to be 90 plus X, correct? Because that's 90 and this I just called X. All right. Now where do we go from here? We'll do the exact same thing on the other side, but before I get to the other circle, I want you to understand one thing, that when I drew a line from O to A, that represents the radius, correct? Radius of the circle. And then I drew the same line from O1 to B. That's also the radius. So that means that this triangle is isosceles. And if it is isosceles, then this angle will also be x. Right? That's the property of an isosceles triangle. And then now I want you to look at these two lines right there. Those create opposite angles. So that means this angle in here is also x. Right? It's opposite to that x right there. And then in a very similar way, when I drew a line from O2 to B, that represents the radius of that small circle. And when I drew another line from O2 to C, that's also the radius. So therefore, this triangle is isosceles. And therefore, this angle in here is x. Okay? And therefore, since this is x and this is 90, this whole angle is 90 plus x. So now I've got to write this out. In order to write a proper proof, you've got to write this out. You can't just label the diagram and say, okay, there you go. So let me write this out. The first one was that this triangle right here, I have labeled the angle x. So I'm going to write all this out in words. The line tangent to the larger circle at A creates a 90-degree angle, meaning angle O1AD is 90 degrees. So that's the first part of my proof. Let angle O1AB equal x. So this angle right here. And therefore, angle DAB will be 90 plus x. Now we start talking about the isosceles triangles and the fact that if you have an isosceles triangle, the other angle will be the same. So since triangle O1AB is isosceles, the angle O1BA is equal to x. And now we have to look at the fact that this angle in here, CBO2, is opposite to this angle, and therefore it's equal to each other. So therefore that angle is x, and that's what I had labeled in earlier. And then we have to talk about how this is isosceles, and therefore this angle is also x. Since triangle CBO2 is isosceles, angle BCO2 is also equal to x. Correct? And then finally we have to explain that this line is tangent at C. Line FG is tangent to the small circle at C, therefore angle O2CG is 90 degrees. And therefore angle BCG is equal to 90 plus x. Okay? I want to keep all this in the same screen. So since this angle is 90 plus x and that angle is 90 plus x, that proves that those two lines are parallel. Since angle DAB equals 90 plus x, which is equal to angle BGC, that proves that the tangent lines DE and FG are parallel, since the alternate angles of parallel lines are equal. And there you go. That is a sufficient proof. And in addition to labeling the diagram, you also have to write it all out to explain it. The circle x minus p all squared plus y squared equals r squared has a center C, and the circle x squared plus y minus p squared equals r squared has center D. The circles intersect at two distinct points, A and B, with coordinates A and B, x coordinates A and B respectively. Prove that A plus B equals P and A squared plus B squared equals R squared. So let's sketch these two circles on a graph and let's get an idea of what's going on in this question. So here's a rough graph. I'm not sure what this graph looks like exactly, but this is a rough idea, and I'll do the labeling. They tell me that there's intersection points of A and B, so I'll call this A, and I'll call this B. And they tell me that the x-coordinates are A and B respectively, so A something, I'll just call it y1, and this one is B something, so I'll just call that y2. They don't give me the y-coordinates. And they tell me these equations, and that's somewhat helpful. It basically tells me that the first one is a circle with the center P0 with radius r. So P0 and radius r, so this is P0 right here, this point. And then the second circle is right here, and that's a center of 0p. So right here, 0p. And anything else? I think that's it. I mean, I guess we could label r. So for example, the distance from here to here is r. But I just don't want to get the diagram too cluttered. All right. So we have to prove a plus b equals p. That's what we have to do first. And then secondly, we have to prove a squared plus b squared equals r squared. All right. Let's do the first one. So the first one should be relatively straightforward because that can be done with just a midpoint. The midpoint of this segment right here. From A to B, that midpoint. And then I will compare that midpoint to the midpoint of D to C, right here. And because of the nature of this diagram, those two are going to have the same midpoint. Because this is essentially a square. The distance r is all the way around. From here to here is r, and then from here to here is r, and from here to here is r. Okay? So here we go. Using the midpoint formula, the midpoint of DC is O plus P over 2 and P plus O over 2, and that is P over 2, P over 2. And then the midpoint of AB, that looks like A plus B over 2, and then Y1 plus Y2 over 2, and that's it. We don't need to simplify it. Now these two midpoints are the same, so that means that this is the same as this. So basically P over 2 is the same as A plus B over 2. And if you multiply both sides by 2, you get P is equal to A plus B. So there you go. We've just proven the first one. Now we have to prove the second one. A squared plus B squared is equal to R squared. And there's several ways of doing this proof right here, but it really just depends on your level of comfortability, which direction you want to do it. I'll just do it my way. My way might seem a little bit longer, but that's okay. I mean, I think as long as you understand it, if you can come up with a shorter way of doing it, then that's perfectly fine. So the first thing, right, is our equations that we are given in the question are x minus p squared plus y squared is equal to r squared. That's the first equation. And the second equation, of course, is x squared plus y minus p squared is equal to r squared. Correct? Now, we are told that these have points that have x-coordinates of a and b. We aren't not told the y-coordinates, we're just told the x-coordinates. So a point of the form a, y1 satisfies the first one, and a point of the form b, y2 satisfies the second equation. All right, so we can get to that later. Now, let's use these two equations to solve for at least one variable. So in the first one, I'm going to isolate for y. So that gives me y is equal to r squared minus x minus p squared, all under the square root sign. And I'll substitute that into this guy right here. So that would be x squared plus r squared minus x minus p all squared minus p all squared like that is equal to r squared. Okay? And then if you multiply this out, you get x squared plus r squared minus x minus p squared minus 2p square root of r squared minus x minus p squared plus p squared equal r squared. Now let's put everything on one side and put the root on the one side like that. And then we can simplify. Hopefully a lot of this will cancel. The x squareds go, the r squareds go, the p squareds go. So that's great. A lot of stuff cancels and we're just left with this. And now we can square both sides to get rid of that square root. And if you do, before we do that, let's just cancel out the 2's and the p's. So then when you finally do square both sides, you'll just have x squared is equal to r squared minus x minus p squared like that. And if you expand this, you will get an expression that you can simplify further. But I don't think we need to do that. What we can do at this point is utilize the fact that we've got two solutions that have a's and b's in them, because we've got to prove a squared plus b squared equals r squared, right? So the good news is that we can put that in here. For x equal a, that's a solution. So a squared is equal to r squared minus a minus p squared. And then x equal to b is also a solution. They tell you that in the question stem. So that means b squared is going to be equal to r squared minus b minus p squared. And if you rearrange these a little bit, you get a squared plus a minus p squared is equal to r squared. And that one, in a very similar way, becomes b squared plus b minus p squared is equal to r squared. And there you go. Since those two both equal r squared, we can set them equal to each other. So I'll do that up here. We got a squared plus a minus p all squared is equal to b squared minus b minus p all squared. Correct? But unfortunately, if you did that, the r's disappear altogether. And we've got to show that r is part of our proof in terms of our final solution, the end result. Okay, so maybe that approach isn't so good. How about if I add those two? I'll keep my r's by doing that. Okay, let's try that approach. On the right side, I'll have 2r squared. On the left side, I'll have a squared plus a minus p squared plus b squared plus b minus p squared like that. Okay, I think this is promising. Let's expand all this out. But before I expand it, I want to use something that I already proved earlier. If you recall, my first proof, I proved that a plus b was equal to p, correct? And if that is the case, then that means that a minus p is equal to negative b, or b minus p is equal to negative a. And therefore, instead of having these p's there, we can put in our values of minus b and minus a. So a squared, but a minus p is right here, negative b. So I got negative b squared like that. And then this guy, b minus p, I can put in my negative a. So there you go. And without, I think, too much difficulty, we're able to pretty much prove this. So we're almost done. We got a squared plus b squared plus b squared plus a squared is equal to 2r squared. And this looks like 2a squared plus 2b squared is equal to 2r squared. And then you divide everything by 2, and that leaves a squared plus b squared is equal to r squared. And there you go. So like I said, there's several ways of doing this. I just like it this way. I really don't think that it's too bad in terms of its length. Can it be done in a shorter way? Perhaps. I think so. But if you can do this in terms of relative comfort, like I have, then, you know, it's perfectly fine, as long as you get the proper result at the end. 9b. If r is fixed and p is then found to maximize the area of quadrilateral CADB, prove that either A or B is the origin. So here's a diagram that's blown up a little bit to illustrate this question. Hopefully this diagram will help. And let's now just concentrate on these formulas. Since they both equal r squared, I'm going to let them equal to each other, right? And when I do that, I will get the following. Let's first expand all this out. And if you do, you get x squared minus 2xp plus p squared plus y squared, and x squared plus y squared minus 2yp plus p squared, like that. And then a whole bunch of things cancel, fortunately. The x squareds go, the y squareds go, and the p squareds go. So all you're left with is 2xp is equal to minus 2yp, like that. And then this basically leaves me with just x equal to y. Yeah, that's it. So that's very helpful, I think. Because what that basically means is that when you have these points that they've given you in the question, A and B have x coordinates, A and B, small a and small b, like that. They don't give you the y coordinate. But since x is equal to y for these two circles, and A and B are on these two circles, the y coordinate is the same as the x coordinate, because x equals y. So that means this is A and this is B. So there you go. Even though we were not told that in the question, we figured it out with the information in the question. So that is the first part of 9b. Now what I want to do is I want to concentrate on these two lines right here. The first line is from A to B, and the second line is from D to C. Okay? Now first let's figure out the slope of A to B, that line right there, from there to there. Well, that's pretty straightforward. Rise over run. The rise is going to be, let's see here, A minus B. The run is A minus B, and that slope is 1. Okay, that was pretty straightforward. Now let's figure out the slope of this guy right here, DC. Okay, the slope of DC, rise over run, so 0 minus P, and then P minus 0. So that's minus P over P, and that's negative 1. Okay, so if DC has a slope of negative 1, and AB has a slope of positive 1, that basically means that since those are negative reciprocals of each other, that AB is perpendicular to DC. So you remember that from like grade 9 probably, that two lines, if they have slopes that are negative reciprocals, those two lines are perpendicular. So that means that AB is perpendicular to DC. So that basically means that these are right angles right here. So right there, those are right angles. Okay? So now we have to concentrate on what they are asking us in part B of this question. They are saying, if r is fixed, that is the radius, and P is then found to maximize the area of quadrilateral CADB. So CADB is this guy right here, CADB. Whatever shape that is, we want to maximize the area of that. And when we do, we will somehow prove that either A or B is the origin. Origin meaning the coordinates is 0, 0. 0, 0, like that. But first, let's concentrate on this. Maximize the area of that quadrilateral. Okay? So we have to maximize that area. So what is that area? Well, since this is a right angle and that's a right angle, I can easily figure out the area in terms of a formula at least. And the area of that whole shape will be, first let's concentrate on this triangle, 1/2 base times height. And the base is AB. And the height, well, the height is from here to here. And I need to label a letter there, right? Let's just call it E, that midpoint right there. Actually, since it's midpoint, let's call it M. I think M is a better letter. Okay? So that height is DM. And then I've got to add this triangle to get the total area. So that other triangle will be 1/2 base times height in a very similar way. That's AB times CM. All right. And let's see here. We get factor this out, AB, and that just gives me DM plus CM. Correct? And the reason I did that is because DM plus CM is just DC. And that just makes our formula a little more simpler. And this is what we have to deal with. We have to maximize this according to the question. Maximize this area of CADB. Okay, let's figure this out. 1/2 AB. A, the coordinates were, I'll just keep it in until I get the coordinates. AB, the length of that line, we are going to have to use that distance formula. So it's going to be A minus B squared plus A minus B squared, all under the square root sign, right? That's the distance formula if you have 2 points. And in a very similar way, DC, let's see here, 0 minus P squared plus P minus 0 squared, all under the square root sign. Okay? All right, so now I can move it up. So this looks like, let's see here, if we expand, we will get 2A squared minus 4AB plus B squared. And then this guy here simplifies to just 2P squared under the square root. Okay, now where do we go from here? Factor out a 2. Sorry, this should be 2 in there. A squared plus B squared minus 4AB under the square root, and then 2P squared like that. Now, at this point, you think, well, geez, it doesn't seem to be going anywhere. But remember, part B comes after part A of this question, and in part A, if you recall, we proved 2 things. First thing we proved that A plus B was P, and the second thing we had proven is that A squared plus B squared is equal to P squared, or R squared, I should say. So, since we already proved those 2 things, we can utilize them. We can put them into our equation. This guy here, I'll put in R squared. Okay? And then, what else can we do here? At this point, you think, well, I'm still going to have this AB. I don't really like that. Too many variables. Okay, I think we can get rid of that. Use this one here. Square both sides. Watch what happens. A plus B squared is equal to P squared, correct? If you square both sides. And if you expand this, you get A squared plus 2AB plus B squared is equal to P squared, correct? Now, A squared plus B squared, if you just regroup it like that, is equal to P squared. And then A squared plus B squared, well, that's just R squared plus 2AB is equal to p squared. And there you go. We can now isolate for 2ab. 2ab is equal to p squared minus r squared, like that. So that allows me to get rid of these ab's. So here I had 4ab, but I've got 2ab, so I'm going to multiply that by 2. So this will be basically minus 2 times p squared minus r squared. Okay? And then at this point, we just got this root 2p squared. Okay, so we're getting somewhere. Okay, don't get discouraged. We're getting somewhere. Area of CADB, and this is what we're trying to maximize. So our next step is to do a little bit of simplification here. 1/2, this is going to be 4r squared minus 2p squared, like that. And then we can probably get rid of a few things in here. In this one here, we can probably factor out a 2 at least. So if we do, we got a root 2 coming out there, and that'll just be 2r squared minus p squared. And then from this guy, we're going to be able to get rid of another root 2, at least bring it out. And then you got that p squared. Now the reason I did that is because if you group this, it becomes 2. And then divided by 2, it's just 1. So all that disappears. And then you're just left with 2r squared minus p squared times the root of p squared. And you can combine those, just put them all under the same square root. So we got 2r squared p squared minus p to the power of 4. Okay, so this is what we're trying to maximize. So if we're trying to maximize that, then we really just need to be concerned with what's under the square root sign. So this basically becomes trying to maximize 2r squared p squared minus p to the power of 4. Now to make things a little bit easier to understand, I'm going to let p squared equal to x. And when I do that, things are going to look a little bit more clearer. So that means this is going to be x squared minus plus 2r squared x. All right? Now, the reason I did that is because this is basically a parabola, if you make it into an equation, right? And like any parabola, if you were to graph it, since the coefficient is -1 there, it's going to be a parabola that basically points downward like that. And its maximum will be the vertex right there. So that vertex will represent the max. So this basically boils down to trying to figure out the vertex of this equation. If you do that, we'll find the maximum value. Okay, so let's try to do that. And if you remember, to find the vertex, we've got to put it in a form of this type, y equals a x minus h squared plus k. If you can put the equation of a parabola into that form, you will know that the vertex is hk. And in our case, that will represent the max. So let's try to get this into this format. Okay, well, how do we do that? Well, you do that by completing the square. And I'm sure by this point in high school math, completing the square is something that you've done several times. So let's do that on this guy right here. So we got minus x squared. I'm going to factor out the minus there. So that will give me just 2r squared x like that. And then to complete the square, you take half of that and square it. So half of minus 2r squared is minus r squared. And if I square that, minus r squared squared is r to the power of 4. And then, of course, I've got to subtract it. That's what it means by completing the square. And then you just leave in the brackets the first 3 terms, and then you kick out the last one. This guy you kick out. But when you kick it out, remember, don't forget the negative there. So that's how you complete the square. And then, of course, this now factors. It becomes x minus r squared, like that, all squared. And there you go. We've got it in this form. And now we can identify the vertex. The vertex, therefore, is r squared, r to the power of 4. Okay? Now, we know that we had let p squared equal to x, correct? So this vertex is basically the coordinates xy, correct, of this parabola. But we let p squared equal to x, so what it really means is that this is p squared. So that means that r squared is equal to p squared. That is essentially what we boiled this down to. So this is a very important finding that's going to help us. Now, if you remember, in our earlier part of question number 9, we have proven that a plus b equals p, and that a squared plus b squared is equal to r squared, correct? Now, we have proven that r squared is equal to p squared. So that basically means that a plus b, which equals p, a plus b is also equal to p squared if you square it. And since p squared is equal to r squared, a plus b all squared is equal to r squared, like that. And then if you expand that, you get a squared plus 2ab plus b squared is equal to r squared, correct? I'll rearrange this a little bit. A squared plus b squared plus 2ab is equal to r squared. A squared plus b squared is r squared based on the proof that we did previously. So we got r squared plus 2ab is equal to r squared. And this leaves me with just 2ab is equal to 0. So that means, therefore, that either a is equal to 0 or b is equal to 0. So either a, which had coordinates a is equal to 0, 0, or b, which had coordinates b is equal to 0, 0. And there you go. That's what they wanted you to prove. They wanted you to prove that either a or b is the origin. And go back and read that question again. Where is it? If r is fixed and p is then found to maximize the area of quadrilateral CADB, prove that either a or b is the origin. And that's exactly what we showed with our big long proof here, right here. Okay, so that takes care of 9b. 9c. If p and r are integers, determine the minimum possible distance between a, b. Find positive integers p and r, each larger than 1, that give this distance. So we are going to use the distance formula to find the distance between a and b. And you remember the coordinates of a was AA. A lot of this is shown in previous parts of this question. And b, the coordinates are BB. So the distance formula would therefore give you a minus b squared plus a minus b squared, all under the square root sign. So if you do all the math here, you get 2a squared minus 4ab plus b squared, all under the square root sign. And we're going to use a lot of the information we already proved. We are going to use the fact that a squared plus b squared equals r squared. This should be a 2 right there. So we got 2a squared plus 2b squared. And we've got minus 4ab like that, all under the square root sign. And 2, we factor out the 2 and get a squared plus b squared. And we got minus 4ab. Now on the side here, I will draw or write in some of the things we've learned so far in our question. The first thing that we proved was that a plus b is equal to p. Okay. We also proved that a squared plus b squared is equal to r squared. And we also proved in 9b that p squared is equal to r squared. Now with this one right here, we can easily just substitute in r squared, so that becomes like that. For AB, it'll take a little bit more work. It'll involve that one right there. So I'm going to multiply that in terms of itself, taking the square of it. And that's going to be a squared plus 2ab plus b squared is equal to p squared. And then a squared plus b squared is r squared plus 2ab is equal to p squared. And then if I put the 2ab on one side, isolate it, I basically get p squared minus r squared like that. So this is minus 4, so I've got to take half of it. So minus 2 times 2ab, which is p squared minus r squared, all under the square root sign. Okay? And then if I simplify this, this is going to give me 2r squared minus 2p squared plus r squared. And this becomes, 2r squared. So this becomes 4r squared minus 2p squared. And if I factor out a 2, I'll just have a root 2 out there, and this will be 2r squared minus p squared, all under the square root sign. And this is my distance of AB. Now they tell you that p and r are integers, right? They tell you that twice actually. So if p and r are integers, then that means that this number in here is also an integer, right? That's the only way this is going to work. And the minimum possible, since we want the minimum possible integer it can be is 1. There's nothing less than 1 that's an integer. Well, there's 0, but the distance can't be 0. So if that is indeed 1, that means that we've got root 2 times the root of 1, and that gives you root 2. And that is the minimum possible distance. So that takes care of the first part of that question. Now we have to figure out the actual value of p and r that give this distance. Okay, I think I can do that. I can keep everything in the same screen here and just do it on the side. Well, how did I get root 2? I set 2r squared minus p squared equal to 1. And I've got to find values of r and p that give me that. And keeping in mind that p and r have to be positive integers. Well, by inspection, I note that if I set r equal to 5, then this would become 2 times 5 squared minus p squared equal to 1. That becomes 5 squared is 25 times 2 is 50. 50 minus p squared is equal to 1. So that means 50 minus 1 is equal to p squared. So 49 is equal to p squared. And therefore p is equal to 7. So there you go. I've got r equal to 5 and p equal to 7. And those are indeed positive integers that are both larger than 1. A school has a row of n open lockers numbered 1 through n, After arriving at school, one day Josephine starts at the beginning of the row and closes every second locker until reaching the end of the row as shown in the example below. Then on her way back, she closes every second locker that is still open. She continues in this manner along the row until only one locker remains open. Define F at n to be the number of the last open locker. For example, if there are 15 lockers, then F at 15 equals 11 as shown below. Determine F at 50. So since F at 50 is not too large of a number, we can write out all the numbers from 1 to 50 pretty quickly and then just do this manually. Okay, let's start our system here. We've got to close every second locker, correct? Every second locker until reaching the end of the row. Okay, so here we go. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50. All right, I got to the end. Now I'm going to go in the other direction, and I'm going to close every second locker. Correct? So I'm going to close 47, 43, 39, 35, 31, 27, 23, 19, 15, 11, 7, and 3. Correct? No mistakes so far? Okay, now we're going to go in the other direction, close every second locker. So that'd be 5, 13, 21, 29, 37, 45. Okay? Now I'm going to go in the other direction, closing every second locker. 41, 25, and 9. Okay? Going in the other direction, closing every second locker. 17, and then 49. And then now going in the other direction, closing every second locker, and that closes 1. So the only one I'm left with is 33. So that basically means that F at 50 is equal to 33. So we did that manually. Now we get to question B. Prove that there is no positive integer n such that F at n equals 2005. Now, we have to sort of get at least some sort of an understanding in terms of what F and n could be. This is obviously some sort of a function. We don't know what that function is. It'd be nice if we did, but we don't. So we have to figure out what F at n is. It's some equation. I don't know. I have no clue what it is. I don't know if it's a linear, or is it a quadratic, what polynomial, no clue. But at least we can get an idea of the pattern by making a little bit of a list. So what I'm going to do is I'm going to make a list of F at n and n for a few of our initial values. And that can be done pretty quickly. So here we go. So here you go. This is a table that shows the values of F at n for n from 1 to 32. And you will see a little bit of a pattern here. And that pattern essentially is that when you have an even number, even numbers are of course all of the form 2m, F at 2m looks like it's always equal to F at 2m minus 1. So for example, if you have F at 8, 8 is an even number, then F at 2m minus 1, which in this case would be F at 7, is the same. F at 8 is 3, and F at 7 is also 3. Correct? In a very similar way, let's say you had F at 16. Well, 2m is 16, so m is going to be 8. So 2m minus 1 is 15. And F at 15 is also the same as F at 16. So f at 16, for example, was 11. F at 15 is also 11. So it looks like this holds true for this pattern. And since that is the case, we only need to look at odd values, since they're always going to be the same as the even values. Okay? So it's a lot of work. I know it's a difficult question, and to get up to this point itself is a lot of work and a lot of time. But this is really the only approach that makes any kind of sense in terms of simplicity. Otherwise, it becomes way too complicated very quickly. Now, of course, I want to figure out an equation for f at n. Okay? It's just like in the movie Theory of Everything when Stephen Hawking wants to figure out an equation that represents everything in the universe. I've got to figure out f at n that represents how to figure out what locker is still open when there's n lockers. But hopefully it's not as difficult as what Stephen Hawking is trying to accomplish, or tried to accomplish in his lifetime. Now, before I get into f at n, I want to talk a little bit about the binary system, because that is what we are going to have to use in order to get f at n, or at least some sort of a system for f at n. Now, if you're familiar with the binary system, that's great, but if you're not, here we go. The binary system essentially means that you can represent any number in terms of the sum of powers of 2. So, for example, if I said to write 25 in the binary system, well, 25 would be 16 plus 8 plus 1, correct? Now, that is 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 0. And instead of writing all these 2's, what they do is they just write 0's or 1's. So, for example, this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, like that. Let me explain that. This first number in this line represents 2 to the power of 0. This one represents 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and so on. If I have a certain power of 2, I put a 1. If I don't, I put a 0. So in our case, when I wrote 25, that was equal to 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 0, correct? So that would be written in binary as 1, 0, 0, 1, 1, like that. So if you were to ask somebody to write 25 in binary, it would be 1, 1, 0, 0, 1, correct? So any number can be written in the binary system. Now, I want you to write 2005, since that is our big number here. Write 2005 in the binary system, because that's going to be at the heart of our question. Well, 2005 first in terms of numbers is 1024 plus 512 in terms of powers of 2, not just any random numbers, powers of 2. 256 plus 128 plus 64 plus 16 plus 4 plus 1, like that. And in terms of power of 2, this was 2 to the power of 10 plus 2 to the power of 9 plus 2 to the power of 8 plus 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of 4, 2 to the power of 2, and then finally 2 to the power of 0. So in binary, it would be written as 1, 1, 1, 1, 1, 0 because there's no 2 to the power of 5, 1, 0 because there's no 2 to the power of 3, 1, 0 because there's no 2 to the power of 1, and finally 1. So there you go. That would be its representation in binary. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? So I hope you understand that, because that's going to be at the heart of our way or system of figuring out f at n. Okay, so here we go now. I'm going to keep that in the screen. I'm going to make a little bit of a table and illustrate a pattern, and then finally we will get to our 2005, which is what they want us to talk about. So I just want you to recall that f at 2m is equal to f at 2m minus 1. That's going to be used a little bit later on. In my table, first I will write f at n up here. I'll use n here. I'm only going to look at odd values. Since we've got this equation, I can figure out the even values pretty quickly. Odd values of n. And then in this column, I'm going to write n in binary, the binary system. And then here is the heart of the question. We are going to try to figure out a system for f at n when n is some number, some odd number. All right, let's go back and let's choose some of the n's and f at n's that we already figured out earlier on up here. All right, we've done so much work, let's just use those. So any of these would suffice, by the way. No matter which ones you choose, it's perfectly fine. It's not like you have to choose some specific ones. Any ones. We're just trying to get a pattern. So I'm just going to choose, let's see, I'll choose 7. I'll go down the list a little bit. I'll choose 13. I'll choose 27. Try to get different values for f at n. So for example, for 7 it's 3, right? For 13 it's 9. For 27 it's 11. So those are different values. I'm also going to choose something that we figured out earlier. You remember we figured out f at 50 in the very first part? We did it manually and we got it to be 33. I'm going to use that as well. Okay? So 1, 2, 3, and 4. I'm going to use those 4 in my table to try to get some sort of a pattern or system. So here we go. So 7, 13, 27, and it was f at 50, right? So 50. And the values for f at n were 3, 9, 11, and 33. Now, before I proceed, remember I can only use odd values, right? Because that's what I'm trying to base my system on. 50 is not an odd number, it's an even number. But no problem, that's where this comes in. We can figure out an odd. If 50 is 2m, that means m is 25. So therefore f at 2m minus 1 would be f at 49, correct? And f at 49 is equal to f at 50. And f at 50 we got as 33. So 49. Okay, perfectly according to our calculations and findings previously. All right, so here we go. We have to put 7 in binary. All right, 7 is equal to 4 plus 2 plus 1. And that is 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. Okay, we don't know any system or pattern yet. Let's just keep going here. 13 in terms of binary is, I believe, 8 plus 4 plus 1. And that is 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 0. 27 in binary is 16 plus 8 plus 2 plus 1, and that is 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 1 plus 2 to the power of 0. All right, I know you're thinking, okay, where is this heading? Is there any rhyme or reason for what you're doing here? Just bear with me here. One more. 49. Well, what is 49? It is equal to 32 plus 16 plus 1 which is 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 0. Okay? And then we have to eventually do it so that f at n is equal to 2005. And that's for some value of n. Okay. Now let's concentrate on these four. Do you see any kind of a system or pattern here? And I will admit, okay, I'm an honest person. I will admit that this is very challenging. And if anybody is able to figure this out, that's just truly excellent. The pattern is as follows. When you create a binary number for each value of n, you have to then omit even numbered powers of 2 in order to get f at n. So I will write that out. Okay? So, for example, when n is 7, 7 is 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0, correct? We have to omit even numbered powers of 2. So I have to take those out. So my even numbered powers of 2 in this case is 2 to the power of 2. All right? And if you do that, you get just 2 to the power of 1 plus 2 to the power of 0, which is equal to 2 plus 1, which is 3. And that is equal to f at n. Do we get 3? Yes, we do. Okay, let's see if this works for the next case. Omit even numbered powers of 2. All right? When n was 13, 13 is equal to 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 0. I have to omit the even numbered power. So I have to take that guy out. If I do, I'm left with 2 to the power of 3 plus 2 to the power of 0, which is 8 plus 1, which is 9. And that is equal to f at n. Is 9 equal to f at n? It is. Let's keep going here. When n is 27, 27 is equal to 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 1 plus 2 to the power of 0. Omit even numbered powers. So I've got to take out that even numbered. That leaves me with 2 to the power of 3 plus 2 to the power of 1 plus 2 to the power of 0. And that is 8 plus 2 plus 1, which is 11. And that is equal to f at n. Is f at n equal to 11? Yes, it is. Now let's go to our last one. Same thing. Omit even numbered powers of 2. When n is 49, we got that equal to 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 0. Our even numbered powers of 2 in this case are just 2 to the power of 4. If you get rid of that guy, you're left with 2 to the power of 5 plus 2 to the power of 0, which is 32 plus 1, which is 33, and that is equal to f at n. And is that true in our case? It is. So that's the system. That's how you figure out f to the power of n. And without a doubt, that's tough. I mean, I don't see anyone other than the most brilliant students being able to figure that out very quickly on a math contest. Now we get to the heart of the question, which is, can we get 2005 for any value of n? Is there any value of n that gives me f at n equal to 2005? All right, let's see. We have to understand, well, how do you get f at n? Well, you have to omit even numbered powers of n from a certain number. Okay? First, let's figure out what is 2005 in terms of binary. Well, 2005 in terms of binary, we did this earlier up. It's actually right here. It's right, I kept it in for a reason. It's 2 to the power of 10 plus 2 to the power of 9 plus 2 to the power of 8 plus 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of 4 plus 2 to the power of 2 plus 2 to the power of 0. Now to get f at n, you have to omit even numbered powers of 2. Correct? But this has even numbered powers of 2. It has quite a few of them, in fact. It's got this one, this one, this one, this one, and this one. So it's impossible to make 2005 as f at n with only odd numbered powers of 2. So I'll write that in. It's impossible to make 2005 with only odd numbered powers of 2. All these f at n's were created with odd numbered powers of 2. You'll see that. See what I mean? All of these. Because you had to omit the even numbered powers of 2. You can't make 2005 with odd numbered powers of 2 because it's got 2 to the power of 10 and to the power of 8 and to the power of 6 and all that. It contains even numbered powers of 2. If you omitted them, you would no longer get 2005. So therefore, no n exists for which f at n is equal to 2005. Now we get to the very last part of our math contest, and that is this one, 10C. So here we go. And 10C states, prove that there are infinitely many positive integers n such that f at n is equal to f at 2005. So my task in the very final part is I've got to choose that f at n and f at 2005 have to be equal. And we've got to prove that this has an infinite number of solutions. Well, we have to basically look at this from the perspective of the previous question, which is that how do we get a value for f at n? You have to omit the even numbered powers, correct? So, for example, if you have f at 2005, like that, you have to first figure out that number in binary and then get rid of the even numbered factors. Exactly what we did in the previous question. So, remember f at 2005, well, n in our case is 2005. And we've got to first put that in binary. So I'll do that, 2005. By this point, you've done this 3 times. This is the 3rd time you're doing this. So you're an expert. 2 to the power of 10 plus 2 to the power of 9, 2 to the power of 8, plus 2 to the power of 7, plus 2 to the power of 6, plus 2 to the power of 4, plus 2 to the power of 2, plus 2 to the power of 0. And then you omit the even numbered powers of 2. So which ones am I going to take out? I'm going to take out the 2 to the power of 10, 2 to the power of 8, 2 to the power of 6, 2 to the power of 4, and 2 to the power of 2. And that leaves me with 2 to the power of 9 plus 2 to the power of 7 plus 2 to the power of 0. And that is 512 plus 128 plus 1. And that is 641. So that basically means that f to the power of 2005 is equal to 641. Okay? That's exactly what I did in the previous part. Now I have to show that f at n is also equal to 641, right? Since f at n is equal to f at 2005. I have to show that there's infinitely many f at n's. Okay, I think I can do that. Is there any other f at n for which I get 641? And the answer is, of course there is, because if you add any single even numbered power, like for example, if you added 2 to the power of 12, when I start using my system, I'm going to take that out. So that will eventually end up with 641. Does that make sense? I hope that makes sense. I'll do it again. Let's say I added any even numbered power to this number. Like if I put in 2 to the power of 12. When I use my system, I'm going to take it out. So in the end, I'll still end up with 641. So what that basically means is that if you have any number of the form, say n is equal to 2005 plus any even numbered power, so 2 to the power of 2m, right? Because 2m is always an even number. That will also give you 641. Okay? So 2m has got to be greater than 10, right? Because when we did 2005 in binary, 10 was our biggest exponent. So 2m has to be greater than 10. Like it can be 12 or 14, like that. So for example, m has got to be greater than 5. So it's going to m can be, say, 6 or 7 or 8 and so on. ... So if n is in this form, then whenever you create f at n, it will be 641. Let's just write that out a little bit. So we got f at 2005 plus 2 to the 2m. If we were to do this in our system, we would basically write it all out, which is going to be 2 to the power of 2m plus 2005 written in binary, right? And then if you eliminate the even numbered powers of 2 using our system, we would get rid of this guy, this guy, this guy, this guy, and this guy. We would also get rid of that one because that is an even numbered power of 2 for any m that is 6, 7, 8, or greater. Correct? So all we would be left with is 2 to the power of 9 plus 2 to the power of 7 plus 2 to the power of 0, which is 641. And this will hold true for all values of m that are 6, 7, 8, and greater. So this holds true for all values of m greater than or equal to 6, and therefore there are an infinite number of values for which f at n equals f at 2005. And that completes number 10.